In this episode of Woodlands on the Web, we're going to be looking at reaction rates, rate laws, and orders of reactions again, but this time with actual examples and a couple of really great summary tables. Okay, so first of all, this is going to show us what the actual concentration versus time looks like for zero, first, and second order. So again, I gave you how to write the rate expressions before, and so again, these are for the decomposition of reactant A, and that's apparently the only thing that's a reactant in these equations that we're talking about here. But basically, we're talking about how the steepness of the curve changes. So how quickly does that rate get to zero is kind of what we're talking about with zero versus first versus second order. So what is the magnitude of that change? Okay. The most helpful things that we get from calculus are the integrated rate laws. So the integrated rate laws can be seen here. And essentially, this is the translation for the graph that we're trying to look at. So not that you have to know calculus for AP chemistry, but if you do understand calculus, you can kind of see how we got to creating these linear graphs from the previous relationships that we discussed. Okay. The main things that we're going to be looking at, though, in our examples is we're going to be looking for things like this, our relative rate versus our concentration. So we can turn that into what we're trying to determine the actual order of the reaction is. So essentially, this first one says if the rate is constant for every different concentration, then it's going to be a zero order reaction. If the rate directly correlates to the change in the concentration, then that's a first order reaction, which is also our best example of nuclear decay half-life. So this is the half-life formula as well. And then finally, if you have a situation where the concentration is, or the rate is changing by a power compared to the concentration. So you can see that 4 represents 2 squared, 9 represents 3 squared. That exponent being 2 is why this would be a second order reaction. Okay, you also do want to be aware of your units, and most of these can be figured out when you actually work examples, but you do want to have a general understanding of what your units would look like. So this is another similar summary table. The only thing here is that we're not showing the actual pictures of the graphs. But again, this is just another way to kind of help you organize that information. So when you're talking about zero order reactions, these statements should basically all be true. Or if you know it's zero order, you know that this is the rate law you want to use. You know if it's first order, then you can find the natural log of the concentration versus time and get the negative slope to find the K value. So if you're given a graph, here you can find the slopes of the graph to find your K value, your rate constant. So there are a lot of different types of problems regarding order of reaction. So let's do a few now to try to get an understanding of some of those. So a lot of your kinetics problems are just going to be data tables with concentration and rates in them, and then you're going to be expected to find a variety of pieces of information related to that data that you've been given. So we're going to do all of these things. We're going to determine the order, write the expression, and determine the value of K using this example for the decomposition of ammonia. Okay, so first of all, finding the order of the reaction. Okay, so the most important thing to notice here is that all of your rates are equal to each other. So if we were using that same method that we had before, where we're trying to say, let's look to see where it doubles, okay? So it doubles from trial 1 to trial 2, but you'll notice that your rate is exactly the same. So if you have 1.5 times 10 to the minus 6 over 1.5 times 10 to the minus 6, that's going to equal 1. And so even though the concentration is doubling, it's doubling with a power of 0. Okay, that's how you get them to equal each other, or so that's how it would equal 1. So trying to find that exponent on the 2, if you have the exact same rate, then it's a zero order reaction. Okay, so that's what allows us to say that it is zero order. Okay, so that's our first question. We can then write the rate law expression. So you're going to have the rate equal to the rate constant times the concentration of the reactant raised to the power of the order of the reaction, which is 0. So in this case, we can actually simplify that to the rate is simply going to equal K, because anything raised to the power of 0 is going to be 1. Because of this, we can also say, therefore, that K is equal to the rate, which is 1.5 times 10 to the minus 6 moles per liter per hour. Okay, so I would actually probably write it this way. Okay, which is the same as molarity per hour. Okay, let's look at one where the rate isn't constant the whole time. So based on what we just did, go ahead and try to use the data that's provided to determine the rate equation, the rate constant, and the overall order of this reaction. So please go ahead and pause the video and try that for yourself first. So I'm going to use the trial 1 and 2 because that's where our concentration doubles. So looking at these numbers, I'm going to first try to determine the order of the reaction. So if I'm using my two rates, I have rate 2, which is 3.2 times 10 to the minus 9th moles per liter per hour, over my first rate, which is 8.0 times 10 to the minus 10. This is where you want to be careful about your exponents, because even if this was a calculator inactive portion, you should be able to kind of recognize this is basically giving you the same thing as 32 over 8. So you're going to get 4, which is 2 to the second power, and therefore that means that this is a second order reaction. Okay? So I like to figure that out first because that's going to be how I figure out how to write my rate expression and my rate constant. So my rate expression is going to be that my rate is equal to little k times the concentration of NaCl raised to the second power. That is my rate law expression. And finally, because I've already determined the order, I can solve for K, which is going to be the rate of my expression over the concentration squared. So I'm just going to use trial 1. Again, it doesn't really matter. So I'm going to use 8.0 times 10 to the minus 10 over 0.1. Okay, so keep in mind this is moles per liter, and this is moles per liter per hour. So that's going to give me a final point of, this is squared because it is a second order reaction. Okay, and that's going to give me a final answer of 8.0 times 10 to the minus 8. And my units for a second order reaction is going to be liters over moles, or inverse moles, over hours, or inverse hours. Okay, so that's going to be my final answer for the value of K. A couple things to give you a little bit more practice is on Science Geek, there are a couple kinetics reviews that you can try. You can get to those either on my campaign guide for this unit, or if you want to go to the OneNote and get it there, those links are live there. As always, thanks for watching, and I hope you learned something.